So in this video I'm going to define capacitive reactance, and this is covered in chapter 33.7 of the textbook. Okay, so what happens if we take a capacitor and we put it in an AC circuit? So we have some AC power source and we just attach it to a capacitor. Well, the voltage across the capacitor, if you think Kirchhoff's loop rule, the voltage across the capacitor has to equal, or the voltage drop across the capacitor has to equal the voltage provided from the power supply. So the voltage across the capacitor is just whatever the maximum EMF is times sine omega t. So the charge, we know but from the definition of capacitance that the charge on the capacitor is proportional to the voltage. So Q is just C times V. So we multiply, so it's going to be changing with time. So we multiply the capacitance by this value of V, and that's going to give us the charge. So it's C times the maximum voltage times sine omega t. And of course, if we want to know current, well, current is just the time derivative of the charge. So if we take the time derivative of Q, this is what we end up with. So we get the capacitance times omega times E max. So we can define that as our maximum current times, well, the derivative of a sine is a cosine, but you can write a cosine as a sine shifted by 90 degrees, or pi over 2 radians. So what this means is that for our capacitor, since there's this shift by pi over 2 radians, it means the current and the voltage do not peak and hit zero and have a trough at exactly the same time like it did for resistors. So in fact, they're said to be out of phase, and in other words, the current hits the peak first, so the current leads the voltage by pi over 2. So we can write an equation similar to what we had for Ohm's law for resistors. Remember, we had V equals I times R was Ohm's law. But we can define something similar where our max current is just the maximum voltage divided by this quantity X sub C, where X sub C is called the capacitive reactance. And capacitive reactance is 1 over the frequency omega, angular frequency omega, times the capacitance. So if you work out the units, it actually has units of ohms, and the capacitive reactance is inversely proportional to the circuit frequency omega, right? So as omega gets bigger, we're dividing by omega, so the capacitive reactance gets small. So this is kind of what it looks like as a function of frequency. So as omega is really, really big, the capacitive reactance gets really, really small. So in other words, our capacitor looks just like a wire, so a resistance of 0. But if omega is really, really small, then the capacitive reactance is really, really big.